Let's do this problem. A farmer wishes to construct two adjacent equally sized rectangular pens. The pens will share a side. The farmer has 3,600 feet of fencing. What dimensions should the pens be in order to maximize area? We can maximize the area of each pen, or we can maximize the area of both. It's going to give us the same thing. Let's draw a quick picture of this to try to get the idea. We're going to have two equally sized rectangular pens that share a side. We want to maximize the area, and we know we have 3,600 feet of fencing. We can either call the length of each pen X or the width of each pen X, it doesn't matter. But I want you to notice, as far as my fencing goes, let's call the length, the point from here to here, X. So notice, as far as fencing goes, we have 3 X's. And if I call this measurement the Y, if each pen has length X and width Y, then we have a total of 4 Ys and 3 X's we're adding up. That is going to equal the 3,600 feet of fencing. We want to maximize the area. We know area of a rectangle is length times width. So that's what we need. 3 X's plus 4 Y's gives me 3,600. That's my constraint equation. And we're maximizing length times width, which is X times Y. All right, so maximize area. Again, this is the area of a rectangle whose length is X and width is Y. The constraint, remember, is the amount of fencing. Fencing, we have 3,600 or 3,600. We had 3 X's plus 4 Y's in our picture. Let's go ahead and solve for either X or Y. I think I'm going to solve for Y here. So 4Y is equal to 3,600 minus 3X. Then divide by 4. I end up with Y equals 3,600 over 4, which is 900, minus either 3/4 or 0.75 times X. I can plug this expression in for Y in the area equation. Therefore, my area equation becomes X times 900 minus 3/4 or I'll just write 0.75 X. Dividing by 4 is a little bit easier because your decimal 0.75 is finite. Dividing by 3, your decimal is 0.6 repeating or 0.3 repeating, depending on what we're doing, and if I'm dividing by 1 or 2. So it's a little bit easier to have these decimals that are finite. Anyways, we do the standard thing, multiply through in order to rewrite your area, then utilize the derivative to give me my critical values. My critical values happen when the derivative doesn't exist or is 0. This derivative always exists, so the only critical value I get is when the derivative is 0. If I solve 0 equals 900 minus 1.5x, I would add 1.5x to both sides, then divide by 1.5 to get x equals 600. This means that the length of the pin should be 600 feet. And the width of the pin I can figure out by utilizing this. If I plug in 600 in for x, 900 minus 3/4 times 600 gives me 450. So the length is 600 and the width is 450. That means the maximum area per pin is 450 multiplied times 600, width times length, which is 270,000. In other words, 270,000. That would be in square feet. So the maximum area per pin is 270,000 square feet. This happens when each pin has width of, again, we called the x the length and the y the width, has a width of 450 feet and length of 600 feet. Just so we're all on the same page, in this case, we shared one of the sides, these two pins shared one of the sides that was the 600, right? The x's were here, the y's were here. If you wanted to, you could double check that if you take 450 times 4, because there's 4 y's here, plus 3 times 600, because there's 3 x's here, you do in fact get 3,600 for the total amount of fencing used. That's how this problem is done.